Good evening from Singapore, good afternoon to Europe, good morning to Chile. We have attendees from all over the world tuning in today. Dear friends, we would like to remind you that this event will be recorded. To the representatives of the Singapore government and the scientific community, friends of the Chilean Embassy, ladies, gentlemen. Welcome to Chilean Astronomy, a window to the universe event organized in partnership between the Embassy of Chile in Singapore and Science Centre Singapore. My name is Yating, Science Educator from the Science Centre Singapore. It is my pleasure to be your MC for today. Our event is part of the UNTAME Festival, Rebooting Our World. For those joining us through the UNTAME Reboot live stream, hello! Our online platform is now in full swing. Do check it out at untame.edu.sg and you'll stand a chance to win attractive prizes, including your very own telescope. Today marks the third day of exploring the wonders of our universe. We will be sharing with you some beautiful images from ALMA Observatory. ALMA represents Atacama Large Millimeter Submillimeter Array. The observatory has a collection of 66 high-precision radio telescopes that work in unison to produce images and discoveries never seen before. ALMA was part of the Event Horizon Telescope collaboration that gave us the first pictures of a black hole. For our first segment, we will be playing a documentary called ALMA, Rebirth of a Giant. This documentary looks at how the COVID-19 pandemic affects the functioning of ALMA Observatory. What happens when we stop 66 antennas located 5,000 meters above sea level? What scientific discoveries have we missed, and what is it like over there now? Sit back and enjoy as we try to answer these questions.
ALMA is a unique telescope in the world. There are many observatories and telescopes in the world, but ALMA is very unique to reveal the cosmic origin.
El hito principal vino en 2019 cuando por fin se obtuvo la imagen, cuando se publicó la primera imagen del agujero negro.
Esta imagen que se logró obtener fue un suceso a nivel mundial y además de gran colaboración. Es la primera vez que lográbamos ver como humanidad qué es lo que era un agujero negro.
Entonces llega esta imagen y viene a probar una teoría que viene cautivando a astrónomos, astrofísicos desde hace mucho tiempo. Entonces para ellos fue la comprobación de algo con lo que ellos soñaban.
Pre-pandemic, in terms of what ALMA was working on, I mean, we had the black hole image from sort of March of the previous year. So in January and February, I was really thinking about how to implement the upgrade of ALMA over the next 5 or 10 years, basically.
En los meses de noviembre y diciembre habíamos tenido un desempeño sobresaliente. Hemos tenido muchas horas, el sistema se había comportado muy bien. Entonces veníamos optimistas, pensando en que bien vamos a poder completar lo que le habíamos prometido a la comunidad científica.
Bueno, en esa época nadie, y ninguno acá, yo creo, en el país ni nada, habíamos escuchado solamente de este virus, pero para nosotros era lejano todavía.
It was somewhere in the middle of March when the schools closed, and then it became really apparent that this was going to have a major impact on our lives here in Chile and the lives of all the staff at ALMA.
Habiendo caso en Chile, esto se iba a diseminar rápidamente, sobre todo en personas que viajamos constantemente en avión, en buses, y que estamos en contacto con muchas personas en los trayectos.
Es un ambiente cosmopolita, tenemos compañeros que son de otros países, entonces también nos empezamos a preocupar y luego fue empezar a ver la parte operativa, cómo nos iba a afectar acá en el observatorio.
Ya a mediados de marzo nosotros ya prácticamente supimos de que esto ya era una pandemia y de que era un inminente cierre del observatorio.
I remember the decision at March the 16th when the central management team meeting, when we discussed the need to shut down the observatory, and certainly very clear in my own mind was the safety and well-being of everybody at ALMA. And so it was a relatively straightforward step to say, I need to consider closing the observatory.
Y finalmente el 16 de marzo, me acuerdo yo, al menos yo bajé el 16, fue que las personas que hacíamos labores administrativas teníamos que abandonar el lugar y ya empezaron a hacer el cierre del observatorio.
El equipo que estaba en sitio en ese minuto en turno es quien tuvo que cerrar todo el recinto, 120 habitaciones que tuvieron que quedar cerradas, con todos sus sistemas apagados, sistemas de aire acondicionado, termos de agua caliente y el campamento que tenemos de soporte para nuestros colaboradores directos. Todo eso tuvo que quedar cerrado.
Con el pasar de los días, el staff de ALMA y contratistas se empezaba a retirar y era bien... No sé si fue triste la palabra, pero el hecho de no saber si los vuelves a ver.
You know, I also kind of felt it too. I know, waving goodbye, the bus is leaving, and I, went down with the first team in San Pedro. That was probably the biggest problem with the shutdown, was the human part, not the technical part.
Cuando me tocó pagar el último equipo, que era el que mantenía viva la conexión a internet, nos desconectamos del mundo. Quedamos aislados, sin telefonía.
Y nuestra comunicación dependía netamente de un teléfono satelital. Y eso yo creo que fue un hito bien impactante porque finalmente apagan todo y nos desconectamos del mundo.
El observatorio ALMA debió cerrar sus puertas debido a la pandemia. Hoy se encuentra vacío, solo los animales silvestres son sus visitas, pues el personal debió evacuar y un equipo de seguridad está a cargo de patrullar sus instalaciones.
Uno de los grandes problemas que nosotros encontramos en ALMA para poder mantenernos vivos bajo el esquema de pandemia era mantener la referencia de tiempo, que es este Maser, el reloj atómico de ALMA. Primero lo dejamos energizado con un banco de UPS, con batería, y aparte se conectó paneles fotovoltaicos.
Pero de repente los equipos fallaban, entonces tuvimos que ir a los 5.000 metros, buscar más paneles solares, armar un conjunto solar, por último hacer visitas, hacer inspección más que nada también.
Las primeras nevazones que hubieron aquí en San Pedro y vientos fuertes, se hicieron equipos de trabajo donde tuve que trabajar junto con Nurikazu, con Stuart, que pensé que en realidad nunca iba a pasar algo así porque son los que están encargados del observatorio, pero junto con ellos estuvimos sellando la antena, estuvimos subiendo los 5.000 metros, preocupados de que no les pasara nada en el momento que no había nadie más, sin saber cuánto tiempo iba a pasar también.
The observatory shut down was something that we'd never done, and when things are shut down for that long of a period without maintenance, it's the risk of how do you get them started back up.
Te encontráis con casi 150 personas y de un mes para otro te encontráis con prácticamente 4 o 5 personas. Entonces es como un sentimiento encontrado, es alguna soledad que al final igual es medio chocante.
Fue fuerte porque acá era un desierto, acá era un desolado. Uno veía gente, se veían los animales que tú ves diariamente, los burros que los vemos todos los días, pero aparecieron animales que no los veíamos hace tiempo también, porque empezaron como a recuperar su espacio. Entonces empezamos a ver otro tipo de animales que sabemos que son de acá, pero que no bajaban a esta altura.
Parecía desierto. Entonces parecía que llevaba abandonado mucho tiempo, los vidrios sucios, los interiores con mucha tierra, polvo que se mete. Entonces parecía en realidad mucho más tiempo el que hubiera estado abandonado. Entonces era un sentimiento bien triste de ver esto tan desierto.
Es como que el tiempo se hubiese detenido, porque encontramos cosas que habíamos dejado en marzo. Documentos, informes. Era volver el tiempo atrás, pero en otras condiciones.
El estar acá, el ver una tremenda instalación, una tremenda inversión de millones de dólares, detenida por un virus, ¿no es cierto?, que está amenazando a la humanidad.
Toda una aventura, la verdad, para nosotros como familia, para mí como trabajador de ALMA también, para mi familia también, el hacerse parte también de mi trabajo, el tener que respetar algunos horarios en donde tengo reuniones, mi hijo que tiene 3 años y medio, que también le parece curioso y me va a ver y a veces aparece en reuniones en pantalla. Y todos nos hemos hecho partícipe de las tareas de la casa y de las tareas también del observatorio. Y en ese sentido también hay tranquilidad.
Te amo, nos vemos mañana. Nos vemos mañana.
So it was a mentally difficult time. People always thinking that their family, but also we need to concentrate our ALMA hardwares and job.
A lot of things happened during the pandemic that were hard. So for me, it was kind of the purpose was a bit gone for a while, because what I really wanted to know when I was a beginning student was how this all got here, and and a little bit of sort of where we came from as life, the fundamental building blocks of life. But for me, it was looking back over in this last year, there was kind of no real hope of answering that question.
Basically, we had not collected data since March, and it delays, the science that one does with ALMA. So, you get the data a year later than you normally would, and you can't make up that time. It's basically lost time on the sky.
So in this science, we really need to catch it in the act of happening. A star exploding, gamma ray bursts, things like that. So these events that happened during the past year when we couldn't observe them we've lost that science maybe forever. Of course, there's other things like comets that don't come around very often. And also there was a very famous star that dimmed dramatically, Betelgeuse, during this time. We couldn't observe with ALMA. So unfortunately, this type of science, we can't just go back and get next year.
It's a little eerie being here, seeing the telescopes standing silently here at 5,000 meters, like silent soldiers on the altiplano. It's a little strange, very eerie, and I have to say I'm really looking forward to the day when we can power them back up again and make them do their thing. I'm looking forward to that day immensely.
Bueno, después de prácticamente 7 meses nos llega la información que el observatorio sí se va a abrir y se va a hacer a andar.
Tuvimos que preparar protocolos en distintos temas, desde el ingreso de las personas al sitio, cómo iba a ser el chequeo, cómo iba a ser el trabajo en la antena.
Cuando dijeron vamos a abrir, va a empezar a llegar gente, viene esa chispa de esperanza, viene esa chispa de que vamos a volver a levantar esto.
Para nuestro equipo, el día más importante del retorno a operaciones fue el día 6 de octubre del año pasado, cuando después de 8 meses sin tener nuestra energía generada, pusimos en una operación las turbinas y ese fue el hito que marcó el retorno a operaciones de todo el observatorio.
Estamos en este momento en lo que es la Power Plant, en la planta de energía que tiene acá el observatorio. Es el corazón, digamos, de todo el observatorio, diría yo. Si no logramos generar con las turbinas, no tenemos cómo poder alimentar las antenas.
En ese momento era un sentimiento de satisfacción, de alegría, de que una vez arrancada la turbina el retorno era inminente.
Este transformador está energizado desde abajo, desde las turbinas. Adelante, Dinko, procede a energizar la antena de A48, por favor. Antena de A48 energizada. Excelente, Dinko, muchas gracias. Primera antena energizada de 66, misión cumplida.
Hoy día estamos todavía en un proceso de recuperación de las antenas para poder retomar las observaciones y que esto siga de manera normal para quienes tienen puesto en esta institución, ¿no es cierto?, mucha expectativa.
Pero ha sido un trabajo titánico de un grupo de gente que no se ve, o sea, nosotros somos el grupo que está acá, pero vemos que está todo Haití en Santiago tratando de levantarnos los sistemas para que podamos tener conexión. La gente del aseo, la gente de los contratistas que nos están dando una mano.
No me imagino otra forma de hacer este retorno. Ha sido tan cuidado.
At the moment, the team are preparing the axles. We're going to take the transporter out for the first time. We'll take the transporter out of the hangar and do another check for any leaks to see if any have developed during the first run. So it's quite an exciting time. Patricio here, one of the transporter operators, and he's using the transporter remote controller to operate. This machine has a lot of complex functions.
La verdad que los riesgos no se conocen porque nunca había estado tanto tiempo detenido.
El proceso de volver para dar inicio al encendido fue complejo desde la casa, ya que tuvimos que hacer como una programación exhaustiva de cómo hacer el encendido de los equipos. Y creo que hicimos un buen trabajo en donde no costó dar inicio a las máquinas y en más de una semana ya tenemos los dos equipos funcionando perfectamente.
I would use two words if I had to. The first one is maybe not all that surprising. I would say survival as a technical telescope, as a entity, as an observatory, and also as the people of ALMA, just making it through this. I think though in the last few months I've started thinking more about kind of a rebirth or revival is the other word I would use to define this last kind of 4 or 5 months, with the similar feeling amongst the staff. So everybody's really motivated to get it back going, and the same as we were breaking new ground with construction. I get the same feeling of that now. So I think it was survival from March to October, and it's been rebirth from October till now.
Cuando comida acá está, nosotros muy contentos volver a casa. Muchas gracias a todos. Ahora este diciembre está más gente. Este turno está total 70 personas. Todavía más, casi mitad. Pero ahora nosotros está con el management team está todo muy contento. Todo cara está feliz. Hoy día está primero día está energizada de antena arriba, 5 antenas. Ojalá que próxima semana movimiento de antena.
I can't believe what an amazing amount of work that's come into bringing this telescope back. It's been such a difficult year, so I know that we can do whatever we set our minds to. So thank you very, very much. Let's go for it and have a really good 2021. And see what we can do in the next few months.
Si bien fue muy complejo el periodo de cierre del observatorio, nos hizo ver que como equipo completo de ALMA, todas las áreas, el nivel de compromiso es bastante alto. Todos hemos estado en base al mejor esfuerzo, trabajando constantemente para el retorno a operaciones una vez dadas las condiciones.
This whole experience of the observatory shut down, the challenges of keeping the observatory safe, and also at the same time thinking about how we get the observatory back to operating again. It's been a huge puzzle. It's required the fantastic efforts of so many people across ALMA. And I have to say, I can't imagine of working with a better team of people to figure out the challenge of bringing ALMA back to doing science again.
ojalá que podamos retomar las observaciones. Estamos todos ansiosos, todos estamos acá por un único objetivo, que es poder brindar datos astronómicos a la comunidad, datos científicos, y ya llevamos un año sin poder hacerlo, así que ojalá que esta noche lo podamos lograr. En esta etapa del retorno a operaciones, estamos ofreciendo a la comunidad un número reducido de antenas, de aproximadamente 32, y varios investigadores accedieron a esas condiciones, así que están agradecidos de que les podamos brindar datos aún con menor cantidad de antenas.
Estamos contentos, es la culminación de un proceso larguísimo que se inició en octubre, casi un año exacto desde que tuvimos que cerrar el observatorio.
Creo que esto demuestra la emoción de todo el equipo dentro de ALMA. O sea, solo nos faltaban 17 horas para haber estado parados un año completo, lo que es terrible para todos. Y creo que ha sido un año muy intenso los últimos meses de preparación para la vuelta de operaciones, y sin olvidar nunca los más de 4 meses de trabajo de la gente arriba en el sitio para levantar el instrumento. Emocionante para todos. Lo hemos conseguido, lo hemos conseguido.
I think this pandemic makes all ALMA team strengths all collaborations and also care each other. So indeed we are become a great team, and everybody indeed want to go back to the operation and back to the sky.
Ninguno en la vida, ¿no? Pensamos vivir una pandemia en que nos dejara absolutamente hacinados en un lugar, escondidos en un lugar por tanto tiempo, y alejados también de nuestro trabajo, que ALMA para todos sigue siendo otra familia.
Tú aquí llegas a ALMA y te vienes a interactuar con otro grupo de personas durante varios días. Entonces, en ese sentido, conocemos una segunda familia, y por lo mismo tenemos que cuidarnos.
Ser parte de esta gran familia de ALMA y para lograr un conjunto de lograr nuevas observaciones, nuevos descubrimientos.
Tiene que seguir, y las proyecciones son tremendas. Yo creo que ya nos dimos cuenta que somos capaces de tanto de parar un observatorio como también volverlo a echar a andar.
ALMA is still the most powerful observatory millimeter wave interferometer in the world, and so that's not going to change. And so when we get back up, hopefully soon, we're still going to be producing great science.
Wow, that was a wonderful film. And we can tell that the staff from ALMA Observatory, we we are so thankful to see that they are so resilient, okay, and they are so happy when the observatory is back in operation again. So thank you to the team who has worked hard so far. Now, for the next segment, we are very proud to introduce Dr. Theodoros Nakos, an astronomer at ALMA, and he is going to be sharing more about his work. Good morning, Dr. Theodoros. Hi, good morning, Dr. Theodoros. Okay, so I think we're having some sound tech problem.
Can you hear me now?
Oh, yes, that's right.
Yes. Okay.
Good
Hi, good
morning.
evening. Hi, how are you?
Good morning. We're good. So we have some audience right here at the Omni Theatre with us, and also some live audience watching us on the Science Center YouTube page. So Dr. Theodoros, would you like to introduce yourself a little bit more and tell us about your work at the ALMA Observatory?
Sure. Well, first of all, let me start by saying how excited I am with this opportunity to talk about the ALMA Observatory. So I am a Greek. I have done an international career since 23 years. I'm at ALMA since 4 years as manager of the data management group, which is in charge of processing the ALMA data. So ALMA is an amazing observatory, and this is not an understatement. Okay, it's the best observatory in radio waves that we have. And it's, of course, not a coincidence that it's in Chile, because Chile is a great place to have observatories, both optical and radio observatories, because of the excellent weather conditions that we have. Okay, so I mean, the video that you showed, it's called The Rebirth of the Giant, but I have a presentation which is called The Birth of the Giant. So actually, part of my presentation will be to show you how ALMA was born. Okay, I had the opportunity to work at ALMA many years ago, in 2011, 2013, where ALMA was a baby, and we had to put all the small bits and pieces that we were receiving at the observatory to create the big observatory that we actually have now. Okay, so I would like to share some material with you that we have, and some of it comes from my personal archive. It's a unique material. Very few people around the world have seen this material, so it's really very excited to be able to share this material with you. And I will start with some videos as well, because I mean, we have our education and public outreach department is doing an amazing work. So I would like to invite the people who are watching us to go and check those videos, because they're really amazing, very well done, and very simple to understand. And I also have a small surprise for you, but we'll keep that for later, okay? So I will share my screen, okay? And for those who want to check our website, I mean, it's almaobservatory.org, and then you can choose the videos you want to watch. We have amazing material, and you can follow us on our social networks like Facebook or Instagram, and other digital platforms like YouTube, Vimeo, etc. Okay, so I will start with a very basic question, because it's important to understand what we call in physics the electromagnetic spectrum. Okay. I'm sorry. Okay, it seems you have not heard the sound of this video. Let me try. Give me a few seconds, please. Okay. Just give me a few seconds. Okay. Okay. All right. Let me see. I'm sure I cannot find how to share my sound. Okay. Okay. I need some help. Hold on, give me a few seconds because the videos we have are really amazing. But maybe, okay. The team in Singapore has the videos. Maybe they want to share the video. Surprised I can't hear. Okay, let's try. Okay, let's try again. Okay. 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 Okay, super. Now, just a very short video about radio astronomy because, of course, we all understand the concept of optical astronomy, so just like taking pictures with our small telescope or with a camera. But radio astronomy has some particularities which are very, very important when we want to study the cold universe. So when I mentioned at the beginning of my presentation that ALMA is the best radio observatory in the world, it was not an understatement. So I'm going to make a simple comparison with what existed around the world in this domain, in this radio astronomy that we call until ALMA. Okay, so ALMA has 66 antennas, as you have heard. And we have in France the ALMA Observatory, which got just 6 antennas, and KARMA in the USA that have 23 antennas, and we had the SMA in Hawaii, USA, that has just 8 antennas. So ALMA has 66 antennas, which is much more, of course, than the 6, 23, or 8 antennas. ALMA has 12-meter antennas, 50 12-meter antennas, and 7-meter antennas as well. But actually, we have only the IRAM that has 15-meter antennas, but KARMA has 3.5 and 10.4 meter antennas, and the SMA had 6-meter antennas. at 2,550 meters, Karma at 2,200 meters, and the SMA at 4,500 meters, while the ALMA antennas are 10 kilometers between ALMA antennas. So the ALMA antennas are moving as a function of time. We have these huge transporters who will take the antennas, lift them up, and move them at different positions. We have around 200 pads where the antennas can sit, and they can move depending on the type of observations we want to execute. So they have the possibility to have them in a very compact array or in a very extended configuration, as we call. And you see, for example, in France, at ALMA Observatory, it was just 700 meters, and at Karma it was 2,000 meters, so the maximum distance of the elevation, and the maximum distance of the SMA in Hawaii 500 meters. So this actually makes ALMA the best observatory in the world, because what we're doing, we're comparing, we're receiving and connecting the light between all these antennas, which are so many, and we have so much better resolution that is uncomparable really with everything that exists until now. So at a fraction of the time, we can study the universe and have much better quality data that were ever taken. It's not an understatement also to say that thanks to the ALMA observations, we are really rewriting the textbooks that talk about radio astronomy. The discoveries that we have done using ALMA are uncomparable in terms of precision and quality of the data with respect to what we had until now. No, the ALMA partnership is a very, very interesting, a very complex partnership, because we have at Santiago de Chile, we have our headquarters where I'm situated at this moment, at the north of the country, around 1,100 kilometers. We have, of course, the OSF, the Operation Support Facility, and a little bit further up, at 5,000 meters, we have the antennas, but we have our ALMA regional centers in North America, in Europe, and in East Asia. So have a large distribution of colleagues around the world with whom we have to collaborate on a daily basis. And that's a satellite image from the OSF that you can see here. You see my mouse, that's this small white spot here on the left of the image is the OSF, and you have to take a 45 minutes drive, respecting, of course, all the safety measures and the speed limits. Believe it or not, we have very strict speed limits because it's a very, very challenging environment, and accidents might take place if we don't take all the safety precautions. And you go up to 5,000 meters where the antennas are located. And if you look here, I mean, what we have put with this point here is the technical building where the array, the correlator, the ALMA correlator, which is the supercomputer that does all the computations, is located. But if you look carefully, you have all these trails, and actually these are positions where the antennas can be located. As I mentioned before, the antennas can move. It's like a lung that inhales and exhales, that expands and contracts. Like the antennas will be moving, we have roughly one antenna move per day, and this is where the antennas have to be located based on what kind of duration we want to reach and take data. Now, this is a very old image from the Operation Support Facility that was taken by me, that was around 2011, 2014, 2011, 2012. Officially, the construction phase of the observatory ended in 2013. So until then, we had many antennas at the OSF, and they were doing many checks of the antennas at the same time. So that's the place where the bits and pieces turned into the most sophisticated sub-meter telescopes, actually. Okay, and so we had three subcontractors that were providing us antennas: Europeans, Japanese antennas, and North American antennas, and all of them were being assembled at the different hangars there. Okay, and we have laboratories, we have workshops, we have, of course, computing infrastructure, and each of the subcontractors were building their antennas, and they were being tested. So you have seen at the video the technical building where we have our laboratories, and so you see some of the antennas there being behind the technical building where they were tested, but many antennas at the background. That was a unique image taken at that time where the antennas were really being assembled, okay? And you have the vendors camps where you have the European, we have the North American, and the Japanese camps where the antennas were being assembled. And that's actually how everything started. So that's why I presented this, I call this presentation the birth of the giant. Actually, everything was coming in small pieces, and we had to put all the pieces together to build the antennas. And this is a real view from the European antennas vendor camp. And actually, you can see the size of the antennas. I mean, each of the antennas, these are the 12-meter dishes, and you see a human next to it, how small he is, the worker is. And of course, all safety precautions have to take place because that was extremely dangerous operation taking place, right? The antennas roughly weighed 120 tons. So, and that's a very important weight, right? So all these pieces were put together, and you see the also for the transporter, they have to come. These are custom-made, built for ALMA. We have 2 vehicles. Each one of them weighs 120 tons and had to lift another 120 tons to take the antennas from maybe from the technical building at 3,000 meters up to 5,000 meters, and that would at the speed of 6 kilometers per hour. These are monsters, really. They have 28 wheels, and they consume 30 liters per kilometer, okay? They're really big. And what's very cool about the transporters, actually, and that's another photo that I took, you have the transporter operator who has in his hands a remote control. So he can be outside the transporter and control this monster with his remote control. Because in some cases, the antennas have to be located so close that it's impossible to do this operation from the inside. So that's me many years ago at 5,000 meters, having my, of course, helmet, protective helmet, and oxygen. We have to breathe oxygen. We have a small backpack with an oxygen bottle, and we have to breathe oxygen. And you see, I mean, the transport is about to position one antenna at one of the pads, and they're so close to the other antennas, right, that if the person doesn't take place with a remote control from the outside, maybe he can damage the other antennas which are neighboring to it. So this is a compact array, extremely compact, and I remind you that the transporter is moving its weight, which is 120 tons plus another 120 tons, and at the precision of millimeters, well, even better than that, the antennas has to be positioned on the pads where they will be sitting before we start taking data. Okay, and this is another picture from the birth of the giant. So at that time we were doing, I was part of the system integration science team. That was the team that was checking the technical specification of each of the antennas, and at some point we were testing. We had a full house. We would test 10 antennas at the same time, and each of the antennas was tested, was verified that it was working properly, and then it was sent to 5,000 meters for start taking data. Okay, and actually, what's amazing about the ALMA antennas is that they're so precise. The precision of the ALMA antennas is 1/1,000,000. So you have this huge 12-meter dish that has a precision 1/1,000,000. 1/1,000,000 would mean, imagine you have a football field which is 100 meters long, and the precision in the surface is better than 0.1 millimeters in a 100-meter field. So the surface has to be so smooth at the level of 0.1 millimeters in a 100-meter field. They're extremely precise, and also they're made of very special materials because they can look at the most distant objects in the universe, but also can point them to the sun, which is extremely hot, and observe as well the sun. There's nothing that can do both types of observations, at any moment. And of course, the temperature variations at the site can go from minus 20 degrees plus to 20 degrees between day and night, or even more. And the antennas had to maintain their server accuracy so can get the best possible quality data. Okay, so that's another very beautiful image of how this giant was born. Every piece was coming individually and they had to be put together, and then we had to assemble the antennas gradually and then test the precision of the antennas. And believe it or not, I mean, the antennas come in slices, and then the slices have to be together and they have to be screwed. In the specific case, we have somebody who goes with a barcode device and checks the specific screw and has to introduce it, turn it a little bit inside or outside to make the whole antenna become uniform. And these antennas have several hundreds of screws, so the whole process may take several hours, and that would be done, had to be done at that time for every antenna, multiple times per each antenna, and there were 66 of them. That was an amazing job, and the people who were there at that time at the construction phase were so motivated, and they were doing that, you know, because they were working for the best observatory in the world. Okay, and that's something very technical. Of course, you don't understand what this means, but that's the dish of the antenna. You send some light to it, and it reflects, comes back, and you know, the more color that you have on the left means the more deformation that you have, and less colors you have on the right means the antenna has reached the specification that we want to reach. And this is a very nice video that shows the work that these people were doing so as to have this giant become what it is now. Well, actually, what you saw in a minute or something was taking something like 5 hours, and that would be done, you know, every day, 3-4 times per antenna. And of course, independent of the weather conditions, a lot of sun, a lot of cold, the antennas had to be corrected for their surface so that they reach the specification. So extremely precise work by extremely motivated people. Now, during the video that you saw, somebody mentioned that the heart of the ALMA Observatory is the turbines that create fuel, but the brain of ALMA is the ALMA correlators. So these are huge, special designed computers that process the signal from all the antennas. These are custom made for ALMA. They are in some huge, rooms at 5,000 meters altitude at the technical building at the AOS, and the calculations they're performing per second, it's 1.7 times 10 to the 16th, so that's 17,000 billions of billions calculations per second. Okay, the approximate cost is $10 million, and they have more than 5,200 signal cables, and we have 20,000 card connections. These are huge computers, and all the signal that comes from the ALMA antennas has to go through the correlators, and they will be processed. And thanks to that information, then we'll be able to create images. So these are how they look like. Huge buildings that have, as said, all this capacity, these correlators to capture in real time, the ALMA data, combine them, and then based on that information later we'll process the data and we'll create beautiful images of the universe. And just a final note, I mean, there's so many challenges to make ALMA work, and of course we take it for granted now that everything is fine, but the extreme weather conditions have an impact both on humans and equipment. You have to do an antenna maintenance, or specific equipment doesn't work properly. You have to go at 5,000 meters, and if it's very, very cold in winter time, you have to wear very heavy clothing and have gloves, but if you have gloves, then you can not do very fine work. So manual intervention at 5,000 meters is not an obvious thing to do. And of course, you have the UV radiation, have very low temperatures, winds, and many other challenges, which of course, the very low oxygen level, which is half as much as we have at sea level. So that's why the safety measures are very important for all ALMA staff when they go and do operations at 5,000 meters, right? Also, supplying power in the most distant parts, 16 kilometers away from the main building, is not easy at all. And also, I mean, ALMA is so precise that we have to correct for the small deformations on the length between the antennas, simply because there are temperature changes. So the ALMA antennas have to send a signal to the coordinator at a very high precision so that the signals are combined and not canceling out each other. You know, there's so many things to talk about ALMA because extremely challenging observatory, but that's what makes it also so unique, because it's actually, based on all these considerations, the best observatory in the world in radio waves. Now, I will just briefly mention a few things about the ALMA science. So what actually you have here, we have what we call protoplanetary disks. So the disks from which stars and planets will form is what we call protoplanetary disks. And actually, what you have gas and dust that will accumulate in specific regions, and they will start rotating, because nothing is static in the universe, everything rotates. And based on the momentum that you have, the angular momentum, actually little by little planets and stars will form. So here what you see in the middle is a star, and around it you have the disk, which is the residuals of the formation of the star. And if you look at this image, that's what we had before ALMA, you know, that was before ALMA. 20 astronomical units means that the size, this corresponds to the distance between the sun and the earth. So you can get a scale about how big these features are, okay? And you can see how much more precise this information becomes when you take data with ALMA. So that goes to previous observatories like SMA, like KARMA, or like interferometers, and this is what you get after ALMA. So that's why when I said that we have to rewrite our textbooks about radio interferometry and radio astronomy, it's because ALMA gives so much more detail that has a huge impact in every area where we want to study the universe using radio data coming from ALMA. So the modeling that goes behind that, then to be able to describe how planets form, for example, has to be used. It has to be have to be updated, those models, using ALMA data, which are much more precise. That's really amazing. What you had before, which is very fuzzy, and something that you have now with ALMA. So you see the different rings. You have the star in the middle, and actually, you can see here, and this is another image using ALMA data in the yellow. You have planets forming there. That would have never been possible with previous radio observatories, because they didn't have that precision. But with ALMA now, you don't only see the star, which is very, of course, well defined here, but you can even see planets forming. And this is combined with other data coming from the Very Large Telescope, another great observatory, actually the biggest observatory, which is located in Chile as well. It's an optical observatory belonging to the European Southern Observatory. So ALMA actually, combined with optical observatories, can give us amazing information about this kind of processes. Okay, and of course, I mean, you have all probably heard about the first ever real image, not a simulation, of a black hole, the Event Horizon Telescope, and that's image of M87, the galaxy M87 that contains the black hole, and that's actually the one you have seen using all data combined from different observatories that participate in this campaign, which was extremely challenging, but gave us this amazing result. And this is what you have done
what you have received without ALMA. Something much more fuzzy and without APEX, which is the small brother of ALMA. It's one antenna next to the ALMA antennas. And you see the amazing difference between what you have had without ALMA playing a major role in this campaign and with ALMA. It's absolutely different what you would have received. And that's where you see that ALMA is so precise that really it will make amazing discoveries. Okay. And that's maybe a little bit difficult to understand as an image, but what you have here is the different elements in the universe. When they vibrate or when they rotate, they create what they call a spectrum. So at different frequencies, they will emit energy. And that's what the spectrum is, right? Like you have the electromagnetic spectrum when you put it through a prism, and you have the beautiful colors of, red, green, blue, yellow of the rainbow. You have something much more precise, much more finite with a better resolution if you use, of course, astronomical instruments. So what we have taken is let's say, some examples of some chemical elements. It doesn't matter what they are. And what we have done, we have taken a spectrum and we have put it upwards, upside down, so I can compare with ALMA, and taken with a space telescope, which is called the Herschel, with a specific instrument, and then we can compare what we receive with ALMA. So you can see that the observations with ALMA give us much more information with respect to what we had with the Herschel image. So, for example, there are areas where you see no emission at all, having, at the same frequencies, at the same energy space, let's say, with the Herschel, and you have huge information using ALMA data. And this means that ALMA allows us to better study any process in the universe because it adds much more information to our knowledge with respect to what they have until now. And I will stop my presentation here. I will stop sharing. Let me go to my, okay. Okay, so that's what I had to present you. And actually, I would like to see if we have the possibility now to do that surprise. I had a surprise for you. Let me check with the team. Okay, so I hope you enjoyed the presentation until now, and the surprise is that actually we're going to visit the ALMA remote control room that we have at Santiago. So, of course, you have seen the video. I gave you the presentation. We talked about ALMA being taken from the OSF, ALMA data being taken from the OSF, which is 1,100 kilometers away from here. But we had this vision a few years ago that observations could be performed remotely. And COVID was the best moment to test all this. So actually, at the premises at ALMA Santiago, we have created an amazing control room from where we can execute observations remotely. Okay, so we're going to visit this control room, and by coincidence, the person who is actually executing observation at this moment is Ludwig. It's one of them array operators that showed up many times at the video that you saw about the rebirth of the giant. So it's a very nice coincidence that Ludwig is here. So I'm going to change my connection from the LAN to Wi-Fi. I have to put, of course, my mask because we have to circulate at the ALMA premises. And I will show you also actually how they look like, the ALMA premises. So bear with me if the quality of the video is not so good, but it's going to be a very interesting, I think, experience that you see how it looks to be operating from 1,200 kilometers away from this amazing ALMA site, okay? I will change my connection now. So maybe we'll lose connection for a few seconds. Okay, already. Let's go. So we have behind me is the corridor. We have many scientists working here. I'm at the second floor of the ALMA building, and we have a beautiful garden at the back. I'm going to go down the stairs. Of course, we needed to have a very beautiful image of one of these protoplanetary disks here that talked before. And of course, we need to have also an image of course, M87, right? So this is our the entrance. And then we have to check our temperature here for COVID. Of course, every astronomer needs coffee, so we have our very nice cafeteria here, respecting the COVID measures. And actually, we're going to move towards the ALMA control room where we're taking the data. In real time, during daytime, we're taking data from here. Okay, so plus permission to enter. So the pilot will have to put his mask on. Here he has to allow us to enter. So, Ludwig, esté con micrófono, no te van a escuchar. Pero han visto el video, el retorno. Así que hasta muchas gracias. So this is Ludwig. I mean, he's one of our best array operators. And you have seen in the video showing up many times. That's a very nice coincidence that Ludwig is now operating the array. So what we have here, we have a very, very advanced control room from where we're taking ALMA data. So actually, I think you can see, what you see here is the ALMA antennas. We can see them in real time from the ALMA remote control room at Santiago. So we're checking the quality of the data, the quality of the observation, the weather conditions, right? We have a series of observations that have to be executed. Of course, we have we're monitoring the weather conditions. We have a weather station there, and we have very, very sophisticated, of course, screen that shows information about the status of the antennas of the receivers that capture the ALMA signal, which observations should be taking place when. So we have a very, very sophisticated control room from where actually we're taking data in real time. Okay, so Ludwig, thanks a lot. Thank you.
Good luck.
Okay, thank you. So this is from where actually data are taken during daytime, and it's a very, very amazing place. And we have astronomers supporting the observations sitting in another room as well. If they have to take some decisions based on weather conditions, they will do it from there. Okay, so I'm going to go back now. I will change my network again. Okay.
you, Dr. Theo, for the very comprehensive presentation that you have for us, and also the tour around your control room. That was really eye-opening for all of us, and we're really enjoying ourselves. So, Dr. Theo, just a couple of quick questions. What made you want to be an astronomer, and how was it like working 5,000 meters above sea level?
Well, actually, that's a very nice question. I mean, I didn't want to become an astronomer at the beginning. I wanted to study physics because I was really fascinated with all the physical, phenomenon. So the blue sky, the change of the colors of the rainbow, and all that stuff. So I studied physics at the beginning, but I had the luck to have very good professors in astronomy from the beginning of my career, and that's how I was fascinated from my first year at university with astronomy. And I took all the courses I could, and then, of course, I did my PhD, and I couldn't have been happier. Now, 5,000 meters, it can be difficult, but even 3,000 meters can be difficult because, I mean, it's extremely dry, so you have difficulty in sleeping at night. That's why, I mean, when ALMA started, I mean, we didn't have this very nice hotel that you see now. You saw people, were sleeping in containers in 2011. And they were very, very dry, so you couldn't sleep at night. So, I mean, I remember the first time I went to the ALMA site, and at that time I was doing shifts of 8 days every 3 weeks. I mean, my skin started bleeding. It was so dry. It was so dry. You had to put a humidifier cream, and that was given to us by the safety department because it was extremely dry. Now we have artificial humidity created. I mean, in the control room, in the rooms where we sleep, so it's much better. But even 3,000 meters, since it's so dry, it's very challenging. At 5,000 meters, you have to use oxygen. Otherwise, it's difficult. Even to sit and breathe and talk, it's not possible. For me, it's not possible. I have to use oxygen.
Wow, that sounds pretty tough working so at a high altitude. So I have another question. So other than the breathing and all that, any other challenges when building the ALMA Observatory?
One of the challenges is I have to think. That's a difficult question. I mean, what makes ALMA so amazing as observatory is the international collaboration. But a very simple challenge that we have is the time difference. Believe it or not, if you have to have colleagues from all around the world, it's impossible to have a meeting with everybody at an hour which is convenient for everybody. So we have to be very careful about when we schedule meetings, because we don't want our colleagues, let's say from East Asia, have meetings very late at night. Because we have 12 hours with Chile, so we could have meetings late at night and early in the morning for them, but then we would leave Europe outside our meetings. So that's a very big challenge, and it's difficult to solve.
Hello. All right, sorry. Okay, so Dr. Theo, so some of us might know, okay, that studying the greenhouse effects in Venus could potentially give us some learning points on our Earth's climate change. Now, as today our event, UNTAME, is themed around sustainability, do you have any data or anything else to show us about the greenhouse effect in Venus?
I don't have data to show, but I know that we have there are many colleagues around the world working on Venus, and actually we had a very controversial incident some time ago. I mean, there was a paper published that said that we had a signal of let's say of biological nature, let's say, a biotrace. That would mean that somehow there microorganisms were creating this kind of signals on Venus. And Venus is a very, very challenging planet because of its conditions. And of course, since it has a very dense atmosphere, you cannot penetrate it unless you use radio waves. Okay, when you take images, let's say in the optical, it's important to see what happens behind the clouds. or after the clouds. That's why it's very important to use ALMA and radio waves in general to be able to probe, to penetrate those clouds and see what's happening at the surface of Venus. I mean, Venus has a temperature of roughly 470 degrees Celsius, extremely hot and very poisonous, so I wouldn't like to be there. Mars is not friendly neither, but it's, let's say, minus 70 degrees. It's a little bit better than Venus. But it's a very, very interesting laboratory, let's say, for understanding the planet formation and why we have planets which have so extreme conditions. So, I mean, the fact that Venus was so closer to the sun made the water in Venus evaporate. And that's why, of course, it ended up, it triggered this greenhouse effect that raised the temperature in Venus so much, and it's so different from planet Earth, our beautiful planet, which has a very comfortable temperature and conditions for living.
And what caused Venus to end up the way it is, and will Earth share...
I lost the sound.
Oh, sorry. Now, can you hear me now?
Yeah.
Yeah. So you did mention that the temperature in Venus is really high. So will Earth share a similar fate? What do you think?
No, I hope not. Well, we know actually that the Earth is doomed, but not because of, well, I won't say because of the humans, not much, but we know because at some point our sun will expand, right? You know, every star has a life, so gets born, then it grows, and at some point will have face death, right? In the case of Sun, it's not going to be a violent death, but it's going to convert itself to a white dwarf. So its outer layers will expand so much that after 4.5 billion years, roughly, so we should not worry about that, it will reach Earth and will evaporate. I mean, the planet will evaporate eventually. Of course, this does not mean we should not respect the planet. On the contrary, we have to be extremely careful about how to treat the planet, and definitely we have to learn examples from other planets as well.
Thank you, Dr. Theodoros. So right now, we are going to open up the question and answer segment to the audience sitting here in the Omni Theater. So anyone have any question for Dr. Theodoros? Okay, if you'd like to ask him a question, you can raise your hand, and our staff here will pass a microphone to you. Okay, so maybe, oh yeah, we have two audience here who would like to ask you a question. So Dr. Theodoros, just give us a moment. We're going to bring our microphone up there for them. All right, so first question, we have a lady.
Yes, hello. Thank you, Dr. Theo. I would like to know which major breakthroughs or any events that have amazed you while looking at in the observatory or a telescope, like in your life. What can you remember as a major discovery? Thank you.
That's a great question. The black hole. I mean, I don't think that anybody, actually, I mean, the teamwork in the black hole had to keep secrecy. That was a very, of course, well kept secret, but that was extremely, let's say, they had to make sure that what they got was right, so they could not make anything public unless they were 100% on what they saw. And we knew there was a press conference, but actually didn't know what I was going to see. So everybody was moved. I mean, that was just an amazing, I mean, in your lifetime, seeing something so amazing, being an astronomer, Einstein talked about this 100 years ago, and see an image of the black hole. I mean, now I think about it, I'm really moved. I mean, I will never forget in my life that moment.
So that's the reason why when Dr. Theodoros, when you were talking about ALMA Observatory, you were so full of passion, and that was really, really nice to see. And we have another audience who have a question for you, gentlemen.
Hi, I'd like to know if the SpaceX satellites, have they affected observation at ALMA in any way?
Yesterday I had a meeting about this, so I mean, actually it's becoming a concern. we have to study this. We have to study this. That's really very, very important question. Thanks for making it. So the astronomical community, of course, has to accept as a fact that satellites will create interference, and this has to be studied. I mean, there are benefits by having satellites creating internet, let's say, for the whole globe. There are many areas, rural areas around the world that will have internet, and that's an amazing thing. It's a fact, so we cannot change that. We just have to mitigate it and come in agreement with these companies, right? And it's different impact for optical or radio observatories who have this to be assessed differently, but awareness is being created, and actually, as literally yesterday we had the first meeting of Chilean community in astronomy to discuss about the impact.
Thank you, Dr. Teo. So we have another gentleman who has a question for you.
Yeah, can you hear me? Yeah. Thank you for the talk, very interesting. So I think you have all quite convinced that ALMA is by far the best telescope. And my question is regarding two of the features of the telescope that you mentioned. One was that has higher resolution, and the other one was faster speed of collection, right? Or something about speed.
Correct.
So
correct.
Maybe related questions. One is, what is the biggest factor of the telescope? Is it the size of the antenna, the number of antennas, or what is it affecting the resolution? And number two, can we add more antennas if we wanted to? ALMA 2.0?
Very nice questions. Congratulations. So, I mean, in astronomy, when we think about telescopes, no matter if it's an optical telescope or a radio telescope, there are two factors which are playing a major role. And both of them are related to the size of the dish, let's say. Imagine that light is like drops of water, because, I mean, it's like the photons we receive, because in astronomy we can use two ways to understand light. One is waves, electromagnetic waves, but photons are equivalent to waves. I mean, that comes from the duality of the light. Okay, so imagine that you collect photons, or let's say light, in a second or 5 seconds, right? It's like drops of water, droplets of water. The bigger the bucket that you have, the more droplets of water or light you will collect per unit of time, per second, per minute, per hour, right? So this means that by collecting more light, you will be able to see fainter objects, okay? That's the concept. So for example, our eye has a lens which is roughly 2.5 centimeters wide and has a very small collective area, but the telescope 1 meter has a much more, a larger collective area. So the amount of light that such a telescope receives is much more than our eye. That's how we see fainter objects. It's exactly the same thing, therefore, with every telescope. Now, there has to be a balance between how much you spend to create a telescope or many telescopes and how much is the benefit, right? So with 66 antennas, we thought that the benefit with respect to what we had before was sufficient for the new science we want to have. But going, let's say, to 100 antennas would be much, much more expensive, and that would make the project extremely difficult in terms of budgetary constraints, okay? So that's why the magic number, let's say, of 66 was chosen, respecting the balance between science, profit, and budget constraints. Now, the second element, one thing about telescopes, is the resolution that you get. So the bigger the lens or the dish, okay, the better the resolution. So this means more finite details you will be able to see. Now, in ALMA, what interferometry does is we combine the signal of all the antennas. So each antenna has a specific field of view on the sky, but by combining all the antennas, we increase the resolutions which we see this field of view on the sky. Okay, so that's why depending on what type of observations we want to perform, we contract or expand the array. The larger the distance between the antennas, the better the resolution we will see. So more details we will see, but at a smaller field of view. Okay, this has an impact. So that's why actually you have up to 16 kilometers distance between the antennas, because then actually you go to very, very fine details that you don't have if you go, let's say, to 1 kilometer or 3 kilometers.
Okay, thank you, Dr. Theodoros. Now, we're going to move the question and answer segment to our online audience. Okay, so we have a couple of questions from our audience tuning in on our YouTube. Now, the first question we have from Harry is that he asked if ALMA conducts training programs or exchange experiences with staff from other observatories or astronomical groups.
So actually, we have trainees that come to work with us and get trained at ALMA in different departments, and they can be either in astronomy or, let's say, software engineers, because I mean, there's a misconception that most people who work observatories are astronomers, and that's actually wrong. We're only 20% of the staff. So most of the people supporting observatories are not astronomers. I mean, astronomers are like small, let's say, small fraction, because I mean, observatories are big production machines of data, and need to have people working in infrastructure, processing. For example, big data. Big data is something which is very, very relevant to us. I mean, we have huge amounts of data coming on a daily basis. High internet speed is needed, and databases. So we have internship from different areas, but sharing experience with other observatories is becoming relevant, because ALMA is the prototype of industrializing astronomy, but in a good sense, you know. So new observatories are going to use ALMA as an example, as a reference for reaching, and let's say, operational level of, you know, like ALMA, of optimizing the operations.
Wow, so this brings some hope to some of our enthusiasts here. They are probably looking forward to joining ALMA next time if there's an opportunity. Now, so we have another, we're going to answer a couple more questions. And one question we have Jia Yi. She asks, how did ALMA manage to capture an image of a black hole? And she wants to say it's really amazing.
Well, that's really amazing. I mean, so when I talked about resolution before, actually, this is exactly very relevant about the image of the black hole. I mean, ALMA is very, very precise, but to go to that resolution, ALMA was not enough. So how to combine all the ALMA data from all the ALMA antennas as if it was one single telescope, and combine it with other observatories that were collecting data around the world at different regions of the world, under different weather conditions and at different moments. So coordinate everything, you know, that all take data simultaneously, but, you know, under different conditions and have different, let's say, configurations of hardware as well, made it very, very difficult. Okay, they had to be extremely precise, all the observations being taken, so that we were able to combine them. And that was one of the big challenges that we had. But as we all know, it was successful, and that's now we have how now we have the first image of the black hole.
So that's actually a lot of work, not just the work from ALMA Observatory, but also from other observatories, just to make sure that the data that was collected is correct, to cross-check.
Yeah.
Right.
That's correct.
So we have another question from our audience right here at the theater. So we have a gentleman here who has a question for you.
Hi, Dr. Theodoros. Thank you very much for your presentation. It was very, very interesting. I think regarding radio telescopes, it's always a bit confusing because we're more familiar with optical telescopes. So I have a follow-on question to the previous gentleman on how it works. And I noted that you have 4 sites in the world with some of these radio telescopes. Do they actually work in conjunction to create even a bigger aperture, or do they just work by themselves only? And a second question is more of an administrative sort of question, is like, who determines what you are observing, and to get the different configurations of your telescope, who actually plans all that? That's very interesting for me. Thank you.
Okay, thanks for the question, which is very, very important as well. So actually, all the ALMA antennas are all situated at the north of Chile, at the Chasmator Plateau. All 66 antennas are there, okay? So the antennas are not distributed around the world. When we worked at the Event Horizon Telescope, we combined data coming from other observatories as well, but they were not part of the ALMA telescope. They were other observatories, okay? But what we have around the world, we have, since ALMA is an international collaboration, we have different organizations financing ALMA because ALMA is a project. So funding comes from Europe, from East Asia, and from North America. But for this exact reason, we also have what we call the ARC nodes. So these are centers that serve the community, the European community, the North American, and the community in East Asia. Okay, so we have people who are working for ALMA as well, but all the antennas are found of ALMA are found at the north of Chile. Okay.
Okay, so Dr. Theodoros, we have one more question, or in fact, the last question from our audience watching YouTube. Okay, so this is a very good question for us to wrap up the session. So Gina asks, what does ALMA expect to find in the future?
Oh, I think probably it's the most difficult question there. Well, I will make a statement which is, let's say, maybe trivial, but I mean, in astronomy, you don't create big jumps from one day to another. I mean, it's a continuous process, right? So, I mean, this depends, of course, on the technology that you have and the computing resource that you have and the money that you have, right? So, I mean, ALMA is on a daily basis improving our knowledge of the universe. I don't expect to wake up one day and find, something that we have never seen before. But I mean, the black hole is one example of things that were just amazing. So I mean, I will not try to disappoint the audience. On the contrary, but I mean, what ALMA is trying is exploring now as a possibility is to become even bigger as telescope. So have some antennas at 32 kilometers far away, so that will improve our resolution even more. And this will allow us to get even more precise images of the universe and understand the process behind them by becoming even more precise.
Yeah, thank you, Dr. Theodoros. Now, in fact, the universe is so huge, so there's always unlimited things that we can find. And that was really a very insightful sharing. Thank you so much, Dr. Theodoros, once again for being here with us. And we do hope that today's live stream, can help to inspire more young people to join astronomy. And not only just in astronomy, so if you're interested in engineering, there is also a chance that you can probably help to build, like our ALMA Observatory. Yes. Thank you. Thank you, Dr. Theodoros. Thank you so much.
Thank you for inviting me. Bye-bye. Bye-bye.
Thank you. All right, so this is the end of our session, but we will continue tomorrow at 6 p.m. online for a roundtable talk with a panel of ladies who will be talking about inclusivity and diversity in astronomy. So in this panel, Chilean leaders will also share their own experiences in STEM with regards to astronomy. Now, in case you have missed other live stream videos, you may head to Science Center's YouTube page to view the recordings. If you have yet to follow our social media pages, do follow us on UNTAME SG on Facebook or Instagram for more updates on the event. We'll be having a day carnival on 20th to 28th November, so do join us for fun activities such as the farmers market and many exciting workshops to choose from. On 3rd to 5th December, you'll get a once-in-a-blue moon chance to experience Science Center After the Dark, a night event featuring exciting performances, activities, and even a foam blaster battle game. So hurry and get your tickets, and in the meantime, don't forget to check out the online game at UNTAME.edu.sg, where you will stand a chance to win many attractive prizes. Last but not least, don't forget Science Center's Observatory Facebook page, SCOB, for more astronomy-related happenings. Thank you so much for tuning in today, and stay safe, everyone. Thank you.